Well, hello boys and girls, this is Daniel for Rock the JVM, and in this video I'm going to talk about the M word. This is a tutorial of monads in Scala that I'm going to try to make as beginner friendly as I possibly can. So this tutorial will involve writing quite a bit of code, so the assumptions that I'm going to make is that you know some Scala fundamentals and obviously that you know how to write generics in Scala. Also, I'm going to kindly ask for your patience in the abstractions that I'm going to derive and that I'm going to talk about, especially towards the end of the video, because the monad laws are inherently annoying. I'm going to try to make them as practical as possible, and so I will recommend that you code alongside me as usual, and whenever you need to go back to the fundamentals of monads, or if you need to refresh your concepts, just return to this video, or if you want to have the code in written form, you can find it at rockthejvm.com/blog at the link in the description of this video. So without further ado, let's get started right in the code. So I'm going to go back to my code editor, assuming that you have yours already set up. So there are millions of monad tutorials on the web. It's not even funny. In fact, it's not funny at all because people make various analogies between monads, Mexican food, endofunctors in the category of psychobabble, and programmable semicolons, and it's very, very hard for a beginner of monads to bridge the gap between all these concepts. And so I'm going to try to make this as practical as possible in the style of why are monads useful to us programmers? Now, unlike burritos and abstract mathematicians, the goal of this video is to write code. So we will show how monads solve programming problems and how they make code easier to understand and how they make us happy and more productive. Now, the idea of a monad is not so difficult, but it's very hard to wrap your head around, especially if you don't know it from the very beginning, because it's very, very general. And once it clicks, it suddenly feels simple and profound, which probably explains the itch of various programmers to write their own tutorials on the subject. Now, my hope is that by the end of this video, you too can go like, hey Daniel, that wasn't so hard. All right, so let's dive right into it. So monads are types which can take some values and do something interesting with them in a certain structure. So 99% of the value of monads lies in their structure, which I hope will become part of your mental model as you start to write more Scala code. So assume, for example, that I want to define a class which prevents multi-threaded access to a value. So I'm going to define a case class. I'm going to call this safe value. I'm going to add a type argument t. I'm going to make it covariant, much like lists, and I'm going to wrap an internal value that I'm going to call private val internal value of type t. All right, so this value is not accessible from the outside world, and I've made it private so that I can do that. Well, this safe value class will have a method called get, which returns a type t, which returns this internal value with a synchronized block. So I'm going to say synchronized, and I'm just going to return internal value. All right. Now, this doesn't really do too much, but just assume that this get method does something interesting. And I've tried to make this interesting by wrapping it into a synchronized block to prevent multi-threaded access to this internal value. Now, bear in mind that multi-threaded access is a much more complicated topic, and it's not the purpose of this video. Just this get method is just a placeholder for something interesting that will return a t. All right, so consider this save value as some sort of a wrapper which returns some form of an interesting value. All right, now assume we also have some external API which has a method. Let's define a method called gimme safe value, which takes a type argument t and a value of type t and returns a safe value of type t. And by the implementation of this method, which you don't need to concern yourself with, I'm just going to return a safe value with value. Right? So assume the implementation here is unknown to you, and you only have access to this method as some form of an external API. Now, the following scenario will go on as follows. I'm going to define a safe string as a safe value of type string, and I'm going to call this quote-unquote external API. So I'm going to say, give me safe value, and let's pass in some string, like Scala is awesome. All right. And we want to process this string by turning it into uppercase. So we want to process the internal value of this wrapper by turning it into uppercase. So the normal pattern or the straightforward pattern to process this string, this internal string, would be to extract it from the wrapper. So I'm going to say, let's call this string as safe string.get, which involves this interesting method that we wrote, which returns this value thread safe. All right, so I'm going to call this extract. Then we're going to transform it. So I'm going to define another value called upper string as string.toUppercase. Okay, so we modify it, and then we are going to wrap it back into another safe value so that we can pass it to some other consumer in our complex infrastructure. So I'm going to call this wrap. I'm going to define another value. Let's call this upper safe string as safe value with this upper string. Cool. So I've extracted the value obtained from an external API, then I've transformed it, and I've wrapped it back into my safe value wrapper. This extract, transform, and wrap pattern is very, very, very common. So this pattern I'm going to call ETW, from extract, transform, and wrap. We're going to see this on and on in this video. Now, instead of doing things sequentially in this way, like val extract, val transform, val wrap again, we can define another method here in this safe value class that will allow us to transform everything in one go. So I'm going to define another method. I'm going to call this transform. I'm going to take another type argument s, which is different than t, and I'm going to take a value function. I'm going to say transformer of type t to safe value s. Why did I do that? The t is the type argument of the internal value that I'm going to wrap. The safe value s will be the end value that I want to get after the ETW pattern. So at the end, I'm going to return a safe value s. And to keep consistency with our thread safety contract of our safe value wrapper, I'm going to say synchronized. And in the synchronized block, I'm going to simply call transformer applied to internal value. Okay, so you can replace this piece of code to whatever is interesting to you, and we will see some examples later in the video. Now, instead of this ETW pattern, we can simply call, let's say, val upper safe string 2 as safe string, the original wrapper, dot transform, and we can pass in a function, underscore to uppercase, and we need to wrap it into another safe value. Now, Scala syntax doesn't allow the underscore here inside this call, so I'm going to name this argument s, and I'm going to pass in the function like this. So given some internal value, I'm going to obtain s to uppercase, and then I'm going to wrap it inside a safe value. So this ETW pattern was compressed into this one line. Now, this pattern of writing code is very, very popular, and you encounter this situation very often in production Scala code. When you want to extract some value, you want to modify it, and then you need to wrap it back so that someone else can use it. This is the ETW pattern, which you can compress into a line that looks something like this. Now, if you have this pattern, you basically created the condition for a monad. And a monad is a type, which I called here safe value for an example. And the monad has two fundamental operations. One is the ability to wrap a value, which is, in my case, a plain value of type t, into my more interesting type, safe value. In object-oriented terms, this is just a constructor. And in functional programming, we call this the quote-unquote constructor, we call this pure or unit. All right, so if you've encountered Haskell or cats in Scala, you've seen the pure or unit application functions that will turn a value into one of these more interesting values of type t. Now, this is the first operation, and the second operation is the ability to transform one of these safe values into another kind of safe value based on a transformation function that looks like this, from t to safe value s. In Scala, we call this bind or flatMap. All right, so I'm going to simply rename this function to flatMap. So we've basically created the conditions for a monad with a constructor, which we call pure, and a flatMap function that has to look something like this. Now, let me give some examples from real life just to reinforce this pattern. So I'm going to start giving some examples. Example 1 for a census application. So let's assume that you are populating a database with people and you have some code that looks like this. I'm going to create a case class called person with a first name as a string and a last name as a string as well. And we want the first name and last name to not be null. So if you want to do a census application, you need to assert that first name is not null and last name is not null either. All right. So if you create a person with null and Jones, then this assertion will throw an exception, and you don't want that. All right. So you need to ensure that first name and last name are not null. And let's assume you have some API. Let's call this the census API. For example 1, census. Okay. And let's assume you have the census API in your application, def get person. Let me scroll down, and I'm going to pass in 2 strings, first name as a string and last name as a string. The trouble is the first name and last name are being populated from the outside, which may be null, and it's your job to test whether they're null or null. And at the end, you'll return a person instance. The general way of or the straightforward way of returning a person with a function that looks like this, where the arguments may be null, would be to write some defensive code. Something like, if first name is not null, well then if last name is not null, then we return a person with first name and last name. Otherwise, I'm going to return null, and otherwise I'm going to return null at the very end. So notice that this is the kind of defensive Java style implementation that we tend to see in Java code, which is very, very hard to read and hard to debug and very easy to nest further. And so if you have the person class to have more constructor arguments, more than just first name and last name, which is often the case in practice, then this code becomes even harder to read. But notice the pattern. We try to extract the first name, we then extract the last name, and if both are not null, then we return a person instance. And so we're wrapping these 2 values into something more interesting, and we can more elegantly solve this with options. So you've probably seen this before. They're like lists, but they have at most 1 element. So I'm going to define another API. Let's call this getPersonBetter with first name as a string, a last name as a string, and instead of returning a person which might be null, I'm going to return an option person. This option person has 2 kinds of potential values. You can return a sum with a person instance, or a none, which is the absence of a person. And we can write it as follows. We can employ this flatMap technique. And so we can say option with first name dot flatMap, and given we have a fname inside, then we are going to do an option with last name, and then I'm going to do a flatMap again. And given a last name that this last option contains, I'm going to return an option with person, fname, and lname. And flatMaps will make sure that the value at the very end is an option of person. So we don't have nested options inside. Much like we had our own flatMap implementation, which takes a function from t to save value s, it doesn't return a save value of save value s, it just returns a save value of a plain value of type s. And so the flatmaps on option will take care to do the same thing. So you've probably seen this before in your Scala code, and we can then reduce this even better with for comprehensions. And so I'm going to copy this method signature, and I'm going to delete these lines. And instead of using flatmaps all over, I'm going to run a for comprehension, which is much more easy to read. So I'm going to say fname in option first name, and lname in option with last name, yield person with fname and lname. Okay, I'm going to name this function getPerson4. And notice that this code is much easier to read because you don't have any more reason to do the null checking yourself. You just delegate the null checking to the option type. So the null checking logic is the interesting part of options, much like thread safety was our interesting part with safe values. So notice that we have an analogous situation with our options as we had with our usual safe values. All right, cool. So this was example number 1 with census, which turns a very defensive and hard to read piece of code into something much more digestible, where you don't even have to think about null checking. All right, I'm going to give another example. Asynchronous fetches. So imagine you're calling some asynchronous APIs for your online store, like fetching from some external resource. So I'm going to define some case classes. I'm going to define a case class user with an ID. And I'm going to also define a case class called product. And this product will have an identifier, usually it's called SKU string, and a price, which I'm going to represent as double, but never, ever, ever, ever represent money with double in your implementations, all right? But I'm going to use double for brevity here. And let's assume that your online store has 2 external APIs. Define getUser with a URL. Let's assume that this URL is the unique URL of a user. And I'm going to pass a string. And this returns a future user. You probably know by now that future is the asynchronous type in Scala. So I'm going to import Scala concurrent future. And let's assume that I'm going to simply return a future with user at ID Daniel, whatever. And just to make this code compile, I'm also going to import the execution context. So I'm going to go at the top and I'm going to say import Scala concurrent execution context with a capital E, implicits with a capital I, and then I'm going to import the global execution context so that the future can actually run. All right, so this is a sample implementation. You might want to call an HTTP API, you might want to call your internal clustering, you might want to inspect some database, whatever. So the only thing that is important is that you return a future user as the result of this getUser method. And in the same style, we are going to define another method called getLastOrder at a user ID. So given a user ID with a string, we are going to return a future product, assuming that this user has ordered a product from our online store. And as a sample implementation, I'm also going to return a future with a product with a SKU, I don't know, 123-456, and the price $99.99. All right, so this is again a sample. The only thing that matters is that this API takes a user ID, which is a string, and returns a future product. Good. Now imagine that I want to get Daniel's last order from the store so that I can send Daniel a VAT invoice or some sort of a notification. However, all I need to know is the URL that Daniel is at. So I'm going to define a val Daniel's URL as mystore.com/users/Daniel, something like that, that I can use to fetch the user. Now what? How do I get Daniel's last product? Beginners usually get stuck at this point. How do I wait for this future after I call getUser so that I can get its value, fetch its value, so extract the future, then transform it into the product that Daniel has ordered, and so I can move on with my life. And so beginners, they on-complete the crap out of this. So the ETW pattern for futures looks something like this. I'm going to say get user at Daniel's URL, and then beginners usually call onComplete, because that's the only kind of API that makes sense, especially when coming from a Java world. You attach all sorts of listeners to asynchronous calls. And so we have onComplete, and in case we have a success with user ID, and let me import success from Scala util. And in case this future completed successfully with a user at this ID is what I call, and this ID is what I care about. And so I want to call get last order, which is yet another future. So I'm going to say val last order as get last order of this ID, and then they onComplete again. So I'm going to say last order dot onComplete. And in case I got a success of a product with a SKU and price, I'm going to compute this VAT included price, which varies per country, but in my country it's P times 1.19. So it's 19% extra tax for VAT. All right. And so we do some things with this VAT included price. And so I'm going to simply pass it on. For example, send Daniel an email. Now, notice we have this ETW pattern over and over again. We are getting a future, and then we want to extract the user from this future once this future completes. And then we want to run another future, and then we want to extract the product out of that future again. And so we transform these two futures by returning the VAT included price, which is our final result. This is really bad, very nested, hard to read, and doesn't cover all the cases anyway, and so you need to account for failures as well. Notice you're following the same pattern over and over again, and you can compress that to flatmaps. And so I'm going to define another val, let's call this VAT included price as getUser at Daniel's URL, and then instead of trying to onComplete, I'm going to simply call flatMap on it. So flatMap, and assuming we have a user inside this future, once this future completes at some point in the future, I'm going to run another future. I'm going to say get last order from user.id. All right, because this is the ID of the user whose future has just completed. And then finally, I'm going to call map, and then I'm going to say underscore price times 1.19. And this will be a future double. Notice we are transforming these futures much like we did with our safe values early at the beginning. So this ETW pattern was compressed to chains of flat maps and maps, which you can also do with for comprehension. So I'm going to call VAT included price, let's call this for, as for comprehension. So for the user in get user at Daniel's URL, and then the order or product, let's call this product in get last order at user.id, we are yielding product.price times 1.19. And this is, again, a future double. So these two implementations here are equivalent. And notice that this code is much easier to read because we are chaining these futures in order. So after you get the user, after you get the last order, then return product.price times 1.19. Good, so I think you're getting a closer picture of the kind of pattern that we want to solve. This extract and transform can be reduced to chains of flat maps and maps or for comprehensions. The third example that I want to show you is double for loops. So lists follow the same pattern, and here's an example. And let's assume you want to return some sort of a checkerboard, that is a Cartesian product, of all possible combinations of elements from two lists. And so I'm going to define eval numbers as list of 1, 2, 3, and I'm going to define another value, let's call this cars, as list of A, B, and C. And you want to construct all the possible combinations as tuples between these three numbers and these three letters. Same pattern. Get a value from the numbers, that is extract. Get a value from cars, extract. Build a tuple from them, transform, and then wrap all of them into a list. And so the ETW pattern is present here as well. Obviously, this is solvable with flat maps. And so we want a checkerboard as numbers.flatMap, and for every number we are going to call cars.map, and for every car we are going to simply return a tuple between the number and that car. And this will be a list of tuples between int and car. All right. So instead of this extract, transform, and wrap again, which in traditional Java would have been done with while loops, in Scala we do this with chains of flatMap and map. Obviously, this is solvable with a for comprehension. And so I'm going to define another value. Let's call this checkerboard2 as a for comprehension. And I'm going to call number in numbers, and then car in cars, and I'm going to say yield a tuple between number and car. And notice this for comprehension is much clearer to see, and this looks oddly similar to Java or imperative loops as a double for loop. The reason why this looks similar is that monads inherently describe sequential ETW computations. So extract this, transform, and then wrap everything into a list. And so if you want to process this further, same thing. Extract, transform, build a tuple, and then wrap everything into a list. So if you got this far, then congratulations. I really appreciate your patience, and I hope these patterns, these examples from real life will identify a common pattern in your Scala code. So whenever you need to extract, transform, and wrap, you probably need a monad, which needs a constructor, which we call pure or unit in Scala, and a transformation function that has to look something like this, which in Scala traditionally we call a flat map, or in other functional programming languages we call bind. Now, we are moving to part 3 of this tutorial, which is the annoying axioms of monads, because we said that a monad has a constructor and a flatMap function, but these two need to work in a certain way. And so monads have some properties. Let's discuss property 1. Property 1 is called left identity, but I don't want to go into psychobabble, so I'm going to give a small example. Let me define a function. Let's call this toConsecutive, which takes a number as an integer and returns the list containing that number and that number plus 1. All right, so two consecutive numbers starting with x. So if you say toConsecutive of 3, you are going to return the list containing 3 and 4. Now, what is toConsecutive of 3? Well, I just mentioned it's list with 3 and 4. Now, I'm going to ask this question differently. What is list of 3 flatMap toConsecutive? I'm going to give you a second or two to think about it, but if you know flatMap on lists, flatMap will simply apply this function on every single element of the list, and it will concatenate all its constituent sublists. And so list of 3 flatMap toConsecutive will be simply list of 3 and 4, because 3 is just the only element of this list, and then we're simply applying the toConsecutive function on it, and we're simply concatenating all these little lists into one big list. And so we are getting the same result. If you simply apply a function to an element, or if you have a monad flatmap that function, you're simply going to get the same thing. And so in more general terms, if you have monad x flatmap f, that is the same as f of x. Now, this is true for any monad, so you can consider option and try and future and list and either. All of them satisfy this property. This is because the monad inherently solves the ETW pattern, because if you had a monad, you would want to extract its value and apply f of x, and so on the right hand side you have f of x. But the purpose of a monad is to circumvent the ETW pattern and just apply flatmap with that function. And so this will return the left hand side. If you want, you can take a couple of seconds to think about it and use this example as a prompter to generalize this property to all monads and try to think in more abstract terms. Now let me go into property number 2. This will probably be the easiest. This is called right identity, but I don't want to go into psychobabble, but I'm going to instead give you some examples. And so let me give a list, let's call this 1, 2, 3, and I'm going to flatmap this list with a function that looks like this. For every x inside, I'm going to create another list. Does this do anything? If you have flatmap on a list of 3 elements, and the function that you are applying is that you're simply wrapping each element into its own list, well, by the implementation of flatmap that you're probably familiar with, flatmap takes all the little lists and concatenates them into one big list. And so at the end, you get list 1, 2, 3. All right, because you have list of 1 concatenated with list of 2 concatenated with list of 3, which gives you one big list which is identical to the original list. So this function is pretty useless in terms of flatmap. In more general terms, if you have monad x flatmap, and for the element inside you do another monad, that's useless and returns monad x. Okay, now let me give this another name so that the x's don't collide. So you have a monad with a value and you flatmap it with a function that returns another monad inside. You don't need that. You are going to simply obtain the same value, but it's important that a monad will respect this property because otherwise the monad will not behave in the way that you expect. All right, so this property 2 I like to call the useless wrap because you're tending to wrap the value inside another monad and you will simply obtain the original monad that you started with. The property number 3 is probably the hardest, but it's also the most important. And this is called associativity, which I like to call ETW, ETW. That is implementing the ETW pattern over and over again. This one is critical. So if you have, let's call this numbers as a list 1, 2, 3. Actually, I have the numbers before, so I'm going to use the same list, but I'm going to define 2 functions. I'm going to define a function incrementer, which takes a number as an int and will return a list of x and x plus 1, much like the toConsecutive method. All right, I've defined it as a function value. And I'm also going to define a value called doubler as taking a number as an int, and it will return a list of x and 2 times x. So much like incrementer, we're simply returning a list containing that number and twice that number. Now, if you apply both transformations in flatmaps on this numbers list, so if you have numbers flatmap incrementer and then flatmap doubler, I'm actually going to print this out. All right, so I'm going to, let me define a main method, and then I'm going to put this function inside so I can run my application. Cool, so let me give the compiler some seconds to run. And so look at the result. We have 1, 2, 2, 4, 2, 4, 3, whatever. So I'm going to paste this here, but I want to separate it. So we have 1, 2, 2, 4, and I'm going to put in some extra spaces here. 2, 4, 3, 6, 2 spaces here, and 3, 6, 4, 8. Why did I put the 2 spaces inside? Because these 4 numbers were generated by the first number 1, because we had incrementer applied to it, and then we had doubler applied to each element of that. And so we had 1, 2, and then 2, 4. The second sublist was generated by the second number, 2. The third set of numbers were generated by the third element in the list. Now, if you are curious enough to decompose this list into its constituent parts, you will notice that these 3 mini lists are the list of, let's call this incrementer 1 flatMap doubler. So these are 1, 2, 2, 4. Then we have incrementer 2 flatMap doubler. And this is the small list 2, 4, 3, 6. And then incrementer 3 flatMap doubler, which is the tiny list 3, 6, 4, 8. So we have the list containing the applications of incrementer flatMap doubler on every single element of the constituent list. And so we have this expression, numbers flatMap incrementer flatMap doubler, as being the same thing as numbers dot flatMap. And for every element inside, let me put a comma here so that my code compiles. For every element inside, we are applying this new transformation, incrementer x flatMap doubler. So I'm going to say incrementer x flatMap doubler. Now, if we print these 2 elements, these 2 expressions here into the console, we should see the exact same result. And my laptop is probably taking off right now. So we have list of 1, 2, 2, 4, 2, 4, 3, 6, 3, 6, 4, 8. And again, 1, 2, 2, 4, 2, 4, 3, 6, 3, 6, 4, 8. So these 2 lists are identical. And I dare say that these 2 lists are actually identical. So I'm going to put in the equal sign here, and I'm going to run this application again, and we are going to see true. And so notice what we've just obtained. We are chaining 2 flatMap calls with 2 different functions, and on the other right-hand side, we have a single flatMap, but with a composite function. So we have incrementer x flatMap doubler inside. In general, for a monad, we are going to have that a monad, let's call this monad value, flatMap with a function and then flatMap with another function, will always be equal to a monad with the same value, flatMap, with a composite function, fx flatMap g. In other words, it doesn't really matter in which order you apply the computations, as long as the function f is applied on every element before the function g is applied on every element. And so the left-hand side applies f on all elements, and then g on all elements. And on the right-hand side, you have f flatMap g applied on every element individually, and then combining them all together. And so these 2 sides of the equal sign are equivalent ways of transforming a monad. And this is very, very important because monads are inherently sequential computations, much like the double for loop as we had in the very beginning. Okay? And so this property is probably one of the hardest to wrap your head around because this describes the sequentialness, is that a word? The sequenceness, probably not a word. The fact that monads are inherently sequential at a very, very, very general level. And so if you want to abstract from the concrete to the very general, I recommend that you go from lists and then to other monads like options and futures, and then validate for yourself that this condition holds true. And it's very important that this condition needs to happen for a structure like this to be called a monad. Alright, so I hope this was useful. I'm Daniel, and you can find this article at rockthejvm.com/blog in written form, and you can follow me on Twitter and LinkedIn with the links in the description attached to this video. Now, I'm dying for feedback, so please leave yours in the comments, and if you like this video, go ahead and subscribe, because more videos like this will be coming soon. Until next time, thank you for watching.